Okay, hi everyone. Let me just check that this is indeed recording and streaming. Okay, looks good. All right, so welcome everyone. We're live now from the kiddies room for reasons that are more fun to speculate about than to explain, so I'll let you do that. So this is the second part of this missing lecture 26, right? Just a lecture from a few weeks ago when I was sick. So you should watch this any point after lectures 1 to 21. So what you should know is already spin systems. If you already went through the spin systems and some examples, then you can do this lecture. Maybe even if you haven't, you'll get a lot out of it, okay? Because it's kind of self-contained. And at any point before the exam. So the next few lectures do not depend on this one, but the exam might. Good, so today we will talk about the harmonic oscillator and then a bit more generally about formalism that can be used to solve this kind of system. So what is the harmonic oscillator? It's now the first take at giving this lecture, so I need to write all the slides. With a little bit of luck for you, there'll be some technical problem and I'll have to do it again, and then it will be much faster. So the harmonic oscillator is, first of all, a system with the following Hamiltonian, as usual. Our kinetic energy, so it's a massive particle, and then a term where you get some constants. We'll get into what these are later. And then here's the big news. So this here is our v of x. So this is our potential. And now it has a special form because unlike most of others that we've seen, it now depends on x squared. So now first I'll tell you why we care about this one, about this, and then I'll tell you a bit more about how to solve it. So first of all, this is the version in 1D. You can do it in 3D as well, and then you have here r squared. And the kind of systems that this models is first, let's look at classical systems, and the most classical one is if you have some weight attached to a spring, okay, and you can pull it horizontally, and of course the spring always pulls it back, and the more stretched the spring is, the larger the force to push it back, right? So it has some rest position in the middle, and this will be your x equals 0, and then the further you pull it, the more the force pulls back. So what happens to such a system? If you've ever pulled a spring, you know that it will oscillate, and then because it has some dampening, it will eventually slow down and then stop, right? But in the perfect conditions, if there was no friction, nothing like that, then it could be described by such a Hamiltonian, of course, in the classical case, and the behavior would be that it just oscillates like this forever. Another one that's maybe more familiar if you had physics in high school is a pendulum, just a simple pendulum. It goes like this. So now instead of x, we have here our angle theta, and it's going to be the same thing. So the higher it is, the slower it gets, right? It gets slower, but the gravitational force is stronger because the height is stronger, right? And then here it's minimum of gravitational force, but and also something with the tensions, but it has maximum speed. So in the positions where it has maximum speed, it has minimum of the other force, that it slows down till it gets here, and then the force pulling him back wins, and it oscillates like this, right? Chook, 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 chook. And if there's no dampening, it will just oscillate like this with a fixed period forever. That's why it's called oscillator and harmonic oscillator. But now, well, what about in quantum physics? Well, in quantum physics, it can describe a few situations. So first, let's see the more complicated one, which is something that we've seen already, which was when you look at the hydrogen atom, what we had was the electrical force between a proton and an electron, right? So now instead of, so they attract each other because they have opposite charges. Instead of this, so take one where they have the same charge, so 2 protons, 2 nuclei, for example, or 2 molecules. And now if we plot, if you remember this effective potential, so this would be x, the distance between them, so r, the distance between them, and this would be the effective potential between them that we have to solve. Then it looks something like, well, there was this term 1 over x squared, goes down, then it has a sweet spot here, and then it kind of goes up, goes up. And where do particles like to be? They like to be in places with that minimize the energy. So around here, around this region here. And in this region, it is the effective potential in this small region looks almost like this here, like the one of the harmonic oscillator. Because what does this look like? This harmonic oscillator, the potential looks like, this is 0 of x, and here v of x, then this looks juk, right? It's a parabola. Now, if you have, for example, 2 molecules or 2 atom molecules, maybe sharing an electron, complicated, but if you have some kind of electric force between them, then the effective potential looks like this. They will want to be in the zone that, you know, the maximum of the wave function absolute value will be around this area, which means the particles want to be more or less at this distance from each other. And in this area, you can model more or less the effective potential by this kind of curve, which is this. Which means that if you learn this from the real Hamiltonian, then you can model the situation with this approximate Hamiltonian, and this tells us a lot about, you know, why molecules have a certain distance between atoms and so on, and what states they have. Good. So that's in quantum chemistry, but also in trapped ions, and I know I've given a few examples about trapped ions a few times now. I've told you before that what they do is they take an ion, which is, it's an atom, they remove some electrons so that it's now charged, and then they confine it with an electric potential in a small region, right? And this small region, in this small region, the V of x is as much as possible close to the harmonic oscillator. And why, again, is because then in this region, we know how to solve this system. So we know what states these ions will have. Okay. So what should I tell you more? Maybe before we get started, I can tell you what this constant W is. So this constant W, like this. So K is the elastic, it's an elastic constant, which depends on the setting. So for example, in the spring, it can depend on the material the spring is made of, or here it will depend on length and masses and so on. Mu is the mass, so that it cancels out with this. It's just more convenient in the quantum case to express it like so. Okay, good. So these are reasons why we care about it, but the main reason why I teach you now is because we know how to solve it. Yeah, there's not so many physical situations that we know how to solve analytically in quantum mechanics, and this is one of them. So let me give you some kind of overview of how it's going to work. We'll prove all of this later. But how it's going to work is through a process called second quantization, which is going to be the following. We will find some operators. Well, it's an operator A and its transpose conjugate, such that we can rewrite the Hamiltonian as some, it's going to be some constant, and then in terms of these operators, plus, it's going to be something like this, okay? For now, it doesn't matter so much. This is going to be an operator called N that we care about, and it will have the following advantage. It's very, very easy to find its eigenstates. So then from here, this is going to work exactly. It's a little bit like spin systems. It's just a subset of the whole machinery of subsystems. So we'll find that the Hamiltonian has some energy levels like this, and that to go up the energy levels, we apply this A plus, and to go down, we apply the A. Just like in spin systems, you have these ladder operators, so here they're going to be the same. And of course, the way we solve it, the way we will solve it once we have this, it's going to be, well, we take the bottom state, we apply the operator must get 0. This gives us a form for this state. And from here, we can build all the others by applying this raising operator. Okay, so I'll just tell you maybe a few more properties that we'll learn. Well, what we learn is that when we find all these eigenstates, like I said, we can go up and down with them. So we can go, and there's going to be some constant. Yeah, a constant that depends on n. Let's call this n plus 1. So this goes up. And when we do the other one, this is going to be some other constant that depends on n. And then it's 1. Okay. Good. So that's how it's going to be. And then it's going to be 0, 1, 2, and so on. So this is what we'll do. But of course, it's going to be a long way to transform this kind of Hamiltonian into something like this, right? So we have to prepare the ground a bit. So first, let us see what would happen if we had some operator that acted like this, that would go, that would have this property. Yeah. So we'll just see what happens in this case. And then we'll relate it to our problem with the harmonic oscillator. So this is a bit more general. It's called ladder systems. So these are systems whenever you have, suppose we have some kind of Hilbert space that is finite, such that when we have, well, it doesn't need to be finite actually, but we take a finite subset, or no, sorry, a countable subset of states within, such that we find an operator which acts like this. So here we have this zero, 1, 2, and so on till infinity. Oh, the other way around. Okay. Right, so we have all of them. So suppose we have it like this, and this function here is still to be determined. We don't know yet. So if we had this, first of all, what is this function given? Well, f of n. You know, this state is normalized. This is not. So this is just going to be n a dagger e, right? So it's just related to the absolute value of this state here. Good. Okay. And this must be, we say that for now that this is going to be a real number. Okay. To be determined. We don't care about it for now. Good. But then from here, we can already infer that if we have the transpose conjugate of the operator, and we apply it in state n, then this must be the same function, but now evaluated on n plus 1. And now n plus 1. And if you think about it, this is exactly what happens in the spin systems when we define the ladder operators, and there's some coefficient that appears here and here. They are different for the A plus and for the A, right? The difference is that now we take from all the spin machinery, we take only the ladder operators. We don't take the X, Z, and Y operators. Good. Why is this true? Well, because if I take an A M, this inner product, so what is this? We have N. Now I have here this operator acting here, gives me the square root of f of m, and here gives me m plus 1. So what is this? This is square root of f of m, sorry, f minus 1. And now we have here n, m minus 1. But this we know is the delta n, m minus 1, right? They need to be the same. Good. But this means that we can rewrite this as square root of f of m plus 1. Sorry. So if n minus 1 is the same as n, then n plus 1 is the same as m. Right? I just rewrote it in this way. Delta m. Yeah, that's right. Yeah, exactly. Okay. So what we get from here, from here it follows that then A applied on n must be the square root of f n plus 1 and n plus 1. And one way to see this is that this thing here if I take the complex conjugate, so this is m n. So it should be this, but now the conjugate of that, right? So, but because f is a real function, it's going to be exactly the same as this. The complex conjugate of a real number, it's the same number again, and it's this. So this tells us what how a plus acts on n, because then if we do the inner product with anything else, it's going to be this delta of n plus 1 and m times this function evaluated on n plus 1. So then the only solution is this. Okay, good. What conditions do we impose on Fn? Note that we're still doing science fiction. We're still saying, look, imagine that there's a Hilbert space and that there exists operators that act like this, and that we want the following, that from this countable subspace, we want that A on 0 on the bottom of the ladder gives a 0. This means that square root of f of 0 must be 0. And, well, we want it to be, f of n be larger than 0 for all n larger than 0. So this is because we're saying, look, imagine there's a Hilbert space, which is infinite, but now inside this infinite Hilbert space, we care about infinitely but countably many subspace states. So it's a subspace where it goes 0, 1, 2. And the idea is that suppose that we are able to go to infinity like this, always going up, which means that all these coefficients must be positive, because I need this to be always be positive, so that it doesn't happen the same as in spin systems where we reach a top, and then if we try to go up, we get to 0. That's the difference between spin and ladder systems. Ladder is just, we could go up infinitely. So this needs to be, okay, good. So these are the conditions so far. So now let's define a new operator in this made-up world. And it's called the number operator. And that's called n for number. And it's just a dagger A. So how does this act on this special state of my ladder? Well, let's see. So it does a dagger A n. So this is a dagger square root of f of n. And -1. And now we apply the A dagger again on this state, so it's square root of f of n. This is the one from before. And I'll write here the new one. So that's going to be square root of f of n minus 1 plus 1. So that's n again. So this whole thing is just f of n. Okay. So this means that the states in my ladder, they are eigenstates of this new operator with eigenvalue f of n, which for now we just say can be any function. This means that we can write this new operator. We just saw its diagonal in this basis, so it's going to be the sum from n equals 0 to infinity of the eigenvalue and then the projector into the eigenstate. Okay, so now we can make our lives easier by choosing the simplest function here, which is just say f of n equals n. Now, it could be that there are some physical systems where you get a more complicated function, but for the ones we'll see, it's perfectly good. So we're still in land of make-believe, right? We're still inventing all these operators. So we just take f of n equals n. It satisfies this condition. F of 0 is 0. F of n is just n, so that's larger than 0 if n is larger than 0. Okay. So we take this. And then we can now simplify all these expressions that we saw before. So now what it takes us is that, in particular, n is sum over n, 0 to infinity of. So n turns out to be an observable, it's Hermitian, which means the following. If you measure this observable, the result, this eigenvalue, tells you in what state you are of the ladder, right? It's like, think of it as just measuring the height at which you are in the ladder. Good. What is the form of A applied on n? This is just then square root of n, n minus 1, and A plus applied on n is square root of n plus 1, n plus 1. You see that here they're already different from spin systems, because in spin systems this function was more complicated. It depended on the other quantum number and so on. So we can still apply most of the formulas that I'll describe if we don't do the simplification. But lucky for us, for the harmonic oscillator, the simplification is good. Good. Okay. So now let's just see one more thing. So let's see what happens if we start at the bottom and we climb up. So then we start with state 0, and then we apply A plus 0. And that gives us, well, this is 1 times state 1. That's just 1 directly. Now, if we apply A plus again, 1, 1, this gives us square root of 2 times 2. And if we apply A plus again, 1, 2, this gives us square root of 3, right? There's always a factor of square root of n every time we go up the ladder. And when we go down, same thing, square root of the higher value. Okay. But this means, in particular, it will be useful for us later that we can, from here, we can rewrite 2 as A dagger plus applied twice on 0 divided by square root of 2. And here 3, well, we start with state 0. We have to apply this A dagger 3 times. And then what's the coefficient we get? So we get square root of 3 from here and square root of 2 from there. So then we have square root of 2 times 3. And so on and so on. The formula, as you might imagine, is that if you want to start at the bottom stage and get to a state n, we need to apply this operator plus n times. And the factor you get is like every time you get square root of the number. So we get overall square root of n factorial. Okay. Good. This will be very useful later when we want to compute the eigenstates of our Hamiltonian. So now there's only one more ingredient we need, which is to look at what the commutator is. And the claim is that A dagger is just the identity. So let's show it. A dagger. So you're just going to see how it acts on the basis element there. It's identity restricted in this subsystem at least. So this is going to be a subspace. So n minus a n. So what is this? So this is a square root of n plus 1, adding up n minus a dagger square root of n minus 1. Don't worry, if n is 0, then this term becomes 0 already, but this one will not be 0. That's not a problem. Then, oh, sorry, I missed something here. This should be n plus 1. This one. Yeah, that's right. Now we apply the operator a here. So we get another factor of n plus 1. And then here we get n again, minus, what did we have here? N minus 1, but now we act with it on it with this operator. So we get a factor n again, square root of n, so we'll get n. Took. And now it's very easy to subtract these two terms because it's just gives us. The only case that would be more tricky is if n is 0, but then this is not a problem because this becomes 1, this is 1. So this is 1 overall. And in this case, we have 0 here, so this term goes away. But the surviving term is already just 1 times n. So 1 times 0. So it also works here. Yeah. Okay. Good. So on these states, it acts like the identity. And we pick these states such that they can form a basis for the whole Hilbert space. And this is now something a bit outside of the scope. But we'll keep this example here. So we saw how they act on these elements, the subspace, and they say this subspace must be a basis. Good. So now from here, we're going to relate it to position and momentum operators. So first, because at the end we want to relate it to the harmonic oscillator. That's right. So we're going to define two operators that act actually a bit like the spin x and y a little bit. So we define the following operators, and then we'll see that they act exactly like position and momentum. So we define x to be alpha could be any real constant divided square root of 2, and now a, let's say dagger. And then our operator p which is going to be a bit complicated. Alpha I square root of 2 a minus a dagger, right? We do it like this. And now we see that they act exactly like position and momentum. So to see this, we're going to look at their commutator. So claim is that xp is going to be exactly I h bar. Oh. And this is the commutator of the usual position and momentum in 1 dimension. If you were in 3 dimensions, we'd have to define these operators a little bit differently. But okay, we do this. So let's just prove it. Maybe I start it on the next page. Okay, so xp commutator is xp minus px, and now we need to replace it with the whole thing. So what was x was alpha over square root of 2 a plus a dagger. I will leave the hats off for now, just so it doesn't get too cluttered, but remember these are operators. of 2, A minus A dagger. This is XP minus PX, so H bar of alpha I square root of 2, A minus A dagger, now alpha square root of 2, A plus. Here, of course, many of these constants cancel out. This is by design, by the way we define these operators. So what are the surviving constants? We have H bar over I 2. Yeah. And now, so this and this, then we have this, 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 and this, and this. So let's write all these terms. Okay. So we have A minus A dagger plus A dagger A. That's this and this. Minus now. Minus A dagger A dagger. Okay. Minus. Now we come here, so we need this, 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 and that. So minus A minus A dagger plus A dagger A plus A dagger. Okay, good. And now the good news is that most of them cancel out as per usual. Quantum mechanics is not that hard. This cancels out, this cancels out. So now we have this one appears twice with the same sign, and this one appears twice with the same sign. So you can get rid of the 2 here over I, and now we have what? Minus A dagger plus A dagger, right? And there was 2 of them, but okay, but this, if I put this minus out here, minus H bar over I, this thing that's left inside here, this is just the commutator, right? Up to a minus sign, which I then take outside. So this is minus A dagger. And now 1 over I is the same as minus I, right? So yeah, that's right. A minus 1 over I is the same as minus I, so the minus cancel out. This is I, H bar. And now this commutator, we defined before that it was the identity, right? Good. Oof. There we are. Good. And this is exactly the commutator of position and momentum. So this means, in particular, that in a one-dimensional system, any one-dimensional system where we have X and P, where we have position and momentum, we can always find these operators A and A. So what are they? And that's the claim. It's just taking this definition and rewriting this as a function of A and A dagger here. Just like when we change bases for states. So the claim is that A is 1 over square root of 2 of X over alpha plus I alpha over H bar P, and A dagger is 1 over square root of 2 X alpha minus I H bar P. Okay, so we need to prove this. In fact, we only need to prove it for the first operator. Oh, sorry, because the second is a dagger, which means it's a transpose conjugate of this, which because X and P are Hermitian, it just means that you flip the sign here, right? On this complex number. Okay. Because note that this is just directly. We can get it directly from above. By taking the complex conjugate, right? Because P equals P dagger and so. Good. So then we only have to prove it. We only need to prove this relation here, so we just do it. And this is very simple, so you can use this time to go get some more tea. So X over alpha plus I alpha over H bar P. And now we just rewrite this in terms of the operators. So what was the definition of X? So we have here 1 over alpha from before. X was alpha over square root of 2 of A plus A dagger. And now we have plus, yes, plus I alpha over H bar. And now the definition of P, which was H bar alpha I square root of 2 A minus A dagger. Okay. And now it's essentially a matter of just canceling out all these constants. And we can do it step by step if you'd like. So all these square roots come out. So overall, we're going to have 1 over 2. Then I'll just even strike them down here. This alphas cancel out. This alphas cancel out. This H bar cancels out. This I's cancel out as well. So then all we have is 1/2 of A plus H dagger plus A minus H dagger, which is just, again, everything cancels out, tuk. And now we have 2A inside and 2A on the outside, and that's just A. Okay, good. We put the hat back just to relax now. Okay, but this is very special because it means that whenever we have a system, it doesn't even have to do anything with position. It just needs to be a continuous infinite system where we have a basis. We define the conjugate basis momentum, right? We know that they satisfy this commutation relation. And from this, we can always build these two operators, which are nice because they have these properties that they act on these ladder states by going up and down. But we still need to apply this to our case now. Okay. So then let's do this. Application. So we had that the Hamiltonian was P squared over 2 mu plus 1/2 of mu omega squared x squared, right? And we want to write this is the goal, is to write it as H bar W and plus identity over 2. Okay. So how do we do this? First of all, we need to choose our constant alpha that appears in all this appears in here in all these definitions, right? We're still free to choose them as long as it results neatly. So we choose alpha to be this h bar over w. And it's just going to be nice to rewrite that 1 over mu is then alpha squared w over h. And like, just trust me, it's good to just be able to look here later. Okay, so we just write it like this. Okay. So first we will just simplify the Hamiltonian, but still keep it in terms of p and x. So first we just simplify the Hamiltonian, so it's 1/2 of, so p over mu is p times this first spring constant, alpha squared w over h bar, p squared plus, now I have mu again, so I get h bar w over alpha squared. Yeah, that's right. X squared. Right, so I just apply this things directly into here and this directly into there. Good. So now we can bring some stuff outside, and we can bring, in fact, the W outside, and we bring an H bar outside because it will be useful later. So then we have alpha squared, divided by H bar squared, P squared, plus X squared divided by alpha squared. And this is really nice because if you remember now the definitions of P and X in terms of A and A dagger, they're very similar to this. We need to move because I'm running out of battery. So take a minute break. I will spare you. Bedroom. Okay. Okay. All right, here we're back. Okay. So we just wrote it in this way because now we have them in a form that makes it much, much easier to transform to the A and A dagger operators. So first, let's just see what P squared is. So we saw that P was what? P was H bar over 2I alpha, A minus A plus. And now we need to take the square of this. So what you're gonna get, we have this I squared gives us a minus sign. Then, oh, there was a square root of 2 there. Then we get 1 over 2 alpha squared. And now we get this thing squared. So A minus A dagger, A minus A dagger. So it's minus 1 over 2 alpha squared. And now the first term is alpha A squared The last term is going to be plus A dagger squared. And then in between we have minus A dagger minus A dagger. Okay. What about x squared? Again, so this was alpha over square root of 2 A plus A dagger, no square plus. And how much is this? That's alpha squared over 2. And now again, we have all these terms. So we have A squared plus A dagger squared plus or A dagger plus A dagger. So this already is looking, if you have the, I don't know, I think by now we've already developed some intuition that lets us look at this and think, there's going to be a lot of things canceling out here. And indeed there is. So we take the whole expression for the Hamiltonian. Let's just copy it from here. Okay, there we are. Now again, it's long and boring. It's more fun if you do it too. So you have alpha squared, h bar squared, and now p squared. So it was this whole thing. Copy. Paste. So this is in brackets. Plus 1 over alpha squared. This is all inside the big brackets. Now my x squared. There you go. Okay, great. So as you can see, it's already going to be very nice because we can cancel out. Wait a moment. Where's the h bar? Ah, we missed the h bar. Here's the h bar square. I forgot about h bar squared. Good. So here's the h bar squared. Good. We needed it because we needed to cancel the other h bar. We need the alpha square to cancel the alpha square, alpha square, alpha square. These two can come outside. So then we have h bar, w. But it's not w, it's an omega, but never mind. By the way, omega is the frequency of oscillation in the pendulum, and so on. So now what we have here inside, a bunch of canceling. So note that here we have a minus sign on top. All these constants we got rid of already. Either they canceled out or I put it outside. So now we just have this term. So minus this term plus this term, right? So then we can look at it. I did it more nicely in the lecture notes if you want to look there. But we can just say, well, these two cancel out because they have this same sign with the minus. There gets opposite signs. And these two, we just have 2 of each, right? So this becomes minus with minus becomes a plus, here another plus. And this term is the same as this. This term is the same as this. Great. So now we have 2 A dagger plus 2 A dagger A. Now, this one we know what to do with. This is our N operator already, right? But this one, we don't know yet what this is. But then it's very easy to say, well, we say, look, A dagger, this is, the commutator is A dagger minus A dagger A. So if I just have the second one, then this is A dagger A plus the commutator. And we know that this commutator is what? That's just the identity, right? Okay. So then this whole thing here, it's going to be what? WH bar over 4. And now we have 2 times A dagger A plus the identity plus 2 times A dagger A. So then the whole thing evaluates to, it's on the one hand, I don't want to clutter this slide too much. On the other hand, it's useful to have all this information together so we can see where it comes from. So let me just put this aside there. Good. There you go. Good. So then remember again, this is N operator, this is N operator. So then what we have, how many N operators we have? We have 2 plus 2, that's 4, cancels out with this 4. How many identities? We have 2 identities and we have 1 over 4 outside. So then it's W H bar N plus 1/2 of the identity. This was the goal. This is what we wanted to do. So we rewrote the Hamiltonian. We rewrote the whole problem from the usual position and momentum to this new set of operators, and we wrote it in terms of the number operator. This whole process is called second quantization, meaning the first time we quantize mechanics, we go from classical position and momentum to the position and momentum operators. And then the next step after that is to let go completely of position and momentum operators for now, and just write it in terms of these ladder operators. It's something that is very useful in a bunch of physics. So if you continue to study, not that I'm trying to bring you from computer science to physics, but if you continue to study physics, you see lots and lots of systems, like from photonics to solid state matter, condensed matter, and so on, where we use second quantization. And the reason we use it is that it does simplify our life a lot. So let me just write why. So because now, so we have H is a constant times N plus constant times the identity. But this means in particular that H commutes with this number operator. And what does this tell us? That the eigenstates of the Hamiltonian are the eigenstates of N. And we know what the eigenstates of N are. We know how to build them. So in particular, they share eigenstates. And what are the eigenvalues? So the eigenstates of the operator are these N states. So on. And the eigenvalues, let's see. Well, we say this is going to be some En. And then, but what is this? So this is H bar W, and now identity, my state N. Well, so let me just write maybe like this. So it's N applied on N plus 1/2 identity applied on N. So this just returns the number N, right? Because it's the eigenvalue of this number operator. The state again, and the identity doesn't do anything. So then what we have is H bar W, and now not the operator, but the number. 1, 2, 3, so on. And now, of course, you can pull all the ends outside. Yeah, so this is h bar w n plus 1/2. And okay, which means that this is our energy, En. Okay. Now, this is very nice. And I'll tell you why it's very nice. It's because it's linear in N. So if I plot, unlike, I don't know, the hydrogen atoms that the energy is changed with N squared, here it changes linearly in N. So if this is the energy, and that's 0, the first state is here. So E0 is h bar w over 2. Then we have E1, which is h bar w 1 plus 1/2. And then they're like all equally spaced, up and up we go. So we have E2 and so on. Meaning that this gap between different energy levels is always the same. So this is always h bar w. Something that's interesting is that the ground state doesn't have 0 energy, it has finite energy. And the other thing is that this makes the system very, very useful. For example, one example is to use it as a little battery. So I want to know what energy I have. I just can put the system in any of these excited states, for example, if I have the tools to do so. And then I know exactly how much energy is stored there. It's going to be at this value here. So if you take the course Advanced Topics in QIT next semester, which I strongly recommend you do, because you have all the background needed for it, one of the things we'll see there is how to use this kind of systems in quantum thermodynamics as energy batteries. So, but we have one thing left to do, which is to find the eigenstates, right? And the way we'll find the eigenstates is going to be the usual stuff, like I said before. We start at the bottom of the ladder. We're going to apply A to see that we must get 0, and then we go up with A plus to find all the other states. And so let's start at the bottom. What we know, we know that A acting on 0 must be 0. But now we're not going to act on the states directly, we're going to act on the wave functions. So we need to know how this operator acts on the wave function. Okay, we can do this. So we know that x takes psi of x to x of x. We know that momentum takes the wave function to minus I h bar dx psi of x. And we know that A, it's 1 over square root of 2. Yeah, this is what we did before, if you don't remember when we found the form for this, plus I alpha over h bar b. So then from here, we can see directly how it acts on the wave function. So it goes to 1 over square root of 2, 1 over alpha, x psi of x. Okay. This is this part here. Oh, sorry, this is this part here from the x operator, plus the part from the p operator. So plus I alpha over h bar minus I h bar d dx. And here we can simplify a little bit. So the h bars cancel each other and the minus I cancels out with the I. So then we just have 1 over square root of 2 of x psi of x alpha plus alpha dtx of okay, good. Okay, so now we need to apply this to the wave function of the ground state. I'll just copy that thing here. New page. So what we know is that A acts on psi of x and takes it to this. And now we need to see that, well, A applied on 0 must give us 0. But what is 0? Well, 0 is a state in a 1D system. So the x look at the basis 0, 1, 2, and so on is different from this basis x. Okay. And then the wave function corresponding to state 0. Yes, please, this is very important. The 0 is not the position 0. Okay? It's the state in the letter. We're going to find out what it is now. It has a wave function like any state in 1D. And the position wave function is explained in terms of position eigenvectors. Good. So what we know is that A applied on this, on this psi 0 of x must be 0 for all x. Right? That's the only way to make this here. Okay. So what does this tell us? You know, we can just copy here. Looks like this, except now it's just special for this function. So this must be 0. Okay, for all x. Okay, so you can shuffle things around a bit. This function is not doing anything here. And we just move just the derivative to the one side as per usual, and we get the following. Dx of phi 0 of x equals to minus x over alpha squared, right? Because there's one alpha here, one alpha there. There's a minus sign when we move one of these terms to the other side. Do it by hand. It's a nice exercise. So this is alpha squared and 0 of x. Okay, good, for all x. And this is an equation, a differential equation that is simple enough that we can solve it. Maybe you remember from calculus, but if you don't, I can tell you the solution. And the solution is that 0 of x is going to be some constant, e minus x squared over 2 alpha squared, which is very nice because this is a Gaussian actually. So this constant a is given by normalization, so you know that the x, the wave function modulus must average to 1, must integrate to 1. So from here, in order to compute the integral of this function, then you get that a is actually 1 over 4 square root of, it doesn't look pretty, but it's the kind of coefficients that we've seen before when we talked about Gaussian wave packets. Right, with this terrible 4th root of things. Okay. What does this look like? It looks a bit like this. What was here being? So if I draw the well in a different color, the well might be maybe like this. And the wave function in white looks a bit like this. So that's what this exponential looks like. It's a bell curve. Okay. Good. So this means we very easily got the ground state, and now we can build all the other steps from here on. So this is bottom, and now going up. Again, one must be a plus 0. In particular, the wave function for this state 1 must be a plus or a dagger acting on the wave function of the 0 state. Next. So how does A act on the wave function? It's very similar. So A dagger is 1 over square root of 2 of x over alpha plus I alpha over h bar p. So this means it maps psi of x to exactly the same as A, except with a change sign, because yeah, here you're going to have a minus sign, so you have a minus sign here. So then you end up with a minus sign there. Did I copy it right? Yeah. So the only difference is that here it's a minus sign. Okay. Sorry. Wait a moment. There's a typo somewhere. Just give me a second. I cannot both be plus A. Let's go back a bit. A plus and the A pluses. Okay, there's a typo in the lecture notes, by the way, which is that this must be a minus sign. Yeah, that's page 15. Okay. So we have this. You know, it's very simple. Psi 1 of x. We don't even have a differential equation. It's very nice. On this psi 0 of x. Well, what did we say psi 0 of x was? A e 2 minus x squared over 2 alpha squared. So then what we have here, 1 square root of 2 x for alpha, and now this thing, a e minus x squared over 2 alpha squared minus alpha x of this thing again, a e minus x squared over 2 alpha squared. And look, now we get to take the derivative. Like, we can use this to prove that the other equation was right, that the other solution was the right solution. Okay, first part stays the same. The second part, we need to take this derivative, so the A constant stays here. Then we get x over alpha squared, and then we get the exponential again. alpha squared there. Oh god. 2 alpha squared. Okay. This is nice again. Things cancel each other out. It's very relaxing when it happens. And then we have a bunch of things you can take outside. Well, in fact, you can take them all outside because now give me a second. Ah, right, of course, there was a minus sign from the x, so this becomes a plus sign. Right, when we take the derivative of this thing, you get minus x times 2. The thing inside. Good. Good. So now what we have here is 2 copies of the same thing. Yeah. It's exactly, we have xa over alpha, and then we have the same exponential again. So this whole thing becomes just there's a factor of 2, cancels with the square root of 2 outside over alpha a x e2 minus x squared over 2 alpha squared. So that's now our wave function for the first excited state. And we can continue like this. If you watch, by the way, the previous lecture, the 26A, you might think, well, this is also a problem with symmetry around the zero of the position. So maybe the parity operator also commutes with the Hamiltonian. So maybe this already tells us that all the eigenstates are either symmetric or antisymmetric, and this is exactly what happens here, right? Look, the first state, this wave function is even, so it's a symmetric state. The second state is the same thing, but now multiplied by x. The rest is just constant. So now it's antisymmetric. The next one is going to be symmetric, the one after antisymmetric, and so on. So the general case, we don't prove it now, but you can try to do it, is that n is given by plus 2dn over square root of n factorial. I mean, this we know, but this we know already. And then one can be shown that this is, it's given by a polynomial of degree n of x over alpha e2 minus x squared over 2 alpha squared. And the nice thing is that for large x, this exponential is always going to suppress this polynomial. Right? Exponentials always grow much stronger than polynomials. You know this if you know any complexity theory. So this means that it looks like this. So if this is the 0, this is x, this is 0. The first wave function is the one we saw before, chuk, centered around 0, of course. And it's an even state. The second one is essentially the same, but multiplied by, so this is size 0 of x. And I'll just draw it a bit further up. Different color. It's going to be the same, but multiplied by x. So if this is 0 here, it's going to be roughly. Well, let me just write down the axis again. This is x. Good. It looks like this. And then the next one, it's going to be looking a bit like, let's do tonight again. like a camel, something like this. And so on and so on and so on. So it's a bit like the wave functions that we saw for the box, except it's a bit more gentle. It's not the cosine, but you know, qualitatively it's close enough. Okay, so what are the takeaway messages from this problem? And with this, we will conclude. Okay, so takeaway messages. So the first thing is that we learn how to do second quantization. And that's taking a Hamiltonian that's written as a function of the position and momentum operators and rewrite it in this way as a Hamiltonian of these operators in a dagger. Satisfying this commutation relation. Right? You'll see later on that this is also very important when you have systems with many particles. I think you see it in quantum mechanics too, because then the n operator counts even the number of particles. So it's used, for example, in photonics. See how many photons there are, also in like lattice systems, and so solid state systems and so on. Good. If we do this, if we can write h equals some constant times n plus some other constant times the identity, where n we know what it is, then we have a ladder system, right? And in this case, we know that we have this energy eigenstates being equally spaced. Sorry, this should be a different constant here. Otherwise, it's a bit boring. Right. So the eigenstates grow linearly, and in particular, the ground state energy is non-zero. And in this kind of systems, it's very easy to compute the eigenstate. So eigenstates start at the bottom like we did, apply A0, and then go up. But yeah, sorry, apply A here and then go up. This is exactly what we did for the harmonic oscillator. By the way, we could have solved the harmonic oscillator in the usual way of just solving this differential equation for stationary states, but this way it's easier, although it was a longer way around. In the end, it's easier. It's more fun, and we learn something that can be applicable in other settings. So that's a net positive. The other thing we learned was the harmonic oscillator in general. In particular, it's a special case. So it's a ladder system, and it starts with this v of x depending W squared. It doesn't matter so much what this constant is, but what matters is it depends on the position squared. So we could draw it like this. This is v of x. V of x here. And now we saw that the energy eigenstates, then they are Very nice. Yeah. So also, we saw this thing here. This is important. The wave function of the eigenstates. And it's important because for low energy eigenstates, most of the wave function is confined in this region, right? So it's almost like having a finite box, because outside here, it's going to decay. You know, there's some polynomial, but there's going to be this exponential suppression. It's always going to win, right? It's always going to go to 0 at infinity. In fact, most of the wave function is inside the box, this imaginary box, right? So I could even draw here the, let me pick a new color. Let me draw here the potential. Maybe it looks like this, right? And here, so now in green, what we have here, these are the different energy eigenvalues, and here's the wave function corresponding to each of them. Right. So most of it's going to be inside this finite region. This is why these kind of potentials are used to confine regions in confine particles in a small region, like the like in trapped ions, as I said in the beginning. In fact, one can compute from that. Well, not directly from this, but you can compute. Because we know the value, we know the operator x, and we know x squared, so we can compute delta x squared. And one can show that this is actually n plus 1/2. And then this h bar to w. So it means that the variance, the dispersion in position, it grows. Well, the square of the dispersion goes linearly in n, so the dispersion itself grows with square root of n. So for these low energy states, we can still find it quite confined inside the box, right? That's why we can trap ions, which are the size of atoms, and we can be pretty sure where they will be if you measure in, a few seconds later. Good. And now I just want to say one more thing, like there's so much we could keep talking about harmonic oscillator. And in fact, if you look in the book, not the lecture notes, the Schumacher-Westmoreland book, there's a chapter called ladder systems, which is about precisely the harmonic oscillator and so on. So one thing that's funny is like, what are lasers? You may have heard this expression that lasers are coherent light. So it's exactly the same. So there is a ladder system, and these are coherent states. What does coherent mean? It's just a superposition with respect to the energy basis. So they can be written as a sum over n of some coefficient. Sorry. There's a typo in election notes. This should be that. Of some coefficient. This coefficient here one can work out. For lasers, it's something like this. So what they are is like a superposition of all this, of all these eigenstates with some cleverly chosen coefficients. And these things, as it turns out, behave like Gaussian wave packets, more or less. That's why you can shoot a laser and see where it's going. So again, there's a lot that could be said about this, but we don't have the time to do it. Good. So then that's all I wanted to say about the harmonic oscillator. It's a lot. I think we went a little bit over the 45 minutes, but it's also because I had to write down everything. So I hope you ran this video at like 1.5 speed, please. Okay, very good. So with this, I say goodbye and see you next week. Ciao.